Hello everyone, my name is Piotr. I'm a software engineer with some experience in distributed systems, an open source enthusiast, a long-time contributor to ScyllaDB, and one of the people responsible for kickstarting the ScyllaDB Rust driver project. Before I dive into details, let me explain why we considered integrating WebAssembly into ScyllaDB in the first place. Our first use case is user-defined functions, also known as UDF. It's a feature in our database that allows defining a function in given language and then using this function when querying data. The function will be applied on the arguments by the database itself and only then sent to the user. It's also possible to express nested calls and other more complex operations with UDF, as you can see on the slide. Until recently, our only supported language for user-defined functions was Lua. It's a decent embeddable language for expressing simple operations, but the support was experimental for a long time, and it actually still is, because of performance, isolation, and security concerns. Hence, we decided to give WebAssembly a try because it's more modern, has more traction, and focuses on isolating the guest code from its host. User-defined functions are a great tool on its own, but their true power lies in being building blocks for user-defined aggregates. Such aggregates consist of at least two functions, one for accumulating the partial result for each row, and one for finalizing the result and transforming it to the output type. You can think of it as kind of a MapReduce operation of sorts. Aggregates are created by first adding appropriate user-defined functions and then declaring which function serves which purpose. By the way, side note, ScyllaDB's implementation extends the CQL protocol by also allowing you to declare an explicit reduce function, which makes it possible for ScyllaDB to automatically distribute the computations to multiple nodes and shards. But that topic is actually extensively covered in another presentation on P99Conf, so make sure you check it out as well. In any case, the potential in user-defined aggregates is quite large. With them, you can express anything ranging from complex statistics, gathering and sampling, to transforming whole partitions into different formats like JSON or rendered HTML pages. And all computations will be performed in the database cluster, while the user only receives a convenient aggregated result, saving time, client-side resources, and even network bandwidth. Once created, user-defined aggregates can be used in select statements as any other function or aggregate, as you can see on the slide. All the meaningful computations happen server-side, and the user is presented only with concise results of the aggregation, which is very convenient. And now a short introduction to WebAssembly to gain some context for the rest of the presentation. It is our new language of choice for implementing user-defined functions. WebAssembly is a format for executable code with emphasis on being easily embeddable, portable, and secure. Its name is actually slightly misleading because it's not only a good fit for web applications, it's a general purpose, efficient embeddable language with a few nice characteristics. One of WebAssembly's core features is isolation. Each module is executed in a sandboxed environment, isolated from the host running the WebAssembly module. Such a limited trust environment is often a key requirement for an embedded language because it reduces the risk of somebody running malicious code from within your project, especially if the code comes from outside the organization. WASM is a binary format simply because that's more efficient, but it can also be expressed in WebAssembly text format, which is more human readable, or rather Lisp developer readable. WebAssembly programs can be written manually, but it happens about as often as writing x86 assembly programs by hand. So technically not never. What's usually done instead is coding in a higher level language capable of compiling to WebAssembly format. There exists a dedicated scripting language for that called AssemblyScript, quite similar to TypeScript, and Its main purpose is bridging JavaScript-based web applications with WebAssembly. Rust also has a quite extensive support for WebAssembly, and it's easy to set up your environment to compile programs to WASM. C++ also has similar capabilities if you use the Clang compiler. Both Clang and Rust toolchains are based on LLVM, and that's why they both benefit from the fact that LLVM can produce WebAssembly binaries. In ScyllaDB, we targeted Rust as our main language for coding WASM-based user-defined functions because it's the most developer-friendly language out there, at least in my opinion. WebAssembly programs are customarily run on a stack-based virtual machine defined by the WebAssembly standard. There are multiple open source projects which implement it, and the one that caught our attention is Wasmtime. It's a WebAssembly runtime coded in Rust, quite lightweight, especially compared to the popular V8 engine, which also supports JavaScript and is generally a Swiss Army knife for web development. But still, Wasmtime, even though it's more lightweight, it has decent performance, lots of features, very active open source development community, and very importantly for us, advanced support for asynchronous execution. I'll explain why async is so important for us later. A side note, another open source project, Wasmer, is also a good candidate for integration, but we chose Wasmtime because we felt especially confident in its support for asynchronous processing. And now let's move to the juicy part of the presentation, which explains how to integrate Rust-based WebAssembly runtime in a very latency-friendly way on top of a high-performance async C++ framework, Sistar, on top of which ScyllaDB, among other nice projects, is implemented. Sistar is a framework designed for high-performance servers, and it's very sensitive to things like latency. Integrating any kind of library with Sistar must be preceded by thorough research whether the library does not use blocking I/O operations and that its long computations can be split into smaller pieces. More specifically, long computations cannot produce stalls. WebAssembly can be used for expressing arbitrary logic, which includes loops and complex programs. So any WASM runtime that aspires to be integrated with Sistar must allow the execution of such programs to be split into manageable pieces, say ones that are expected to run in less than half a millisecond or a single millisecond. Taking longer time may mean that we miss a latency requirement on another task, and that is simply unacceptable. Then Sistar, which is almost an operating system on its own, it also manages its own memory allocations. Therefore, a library gets extra points for being able to accommodate and use Sistar's allocation mechanisms instead of its default ones. And finally, we want as little overhead induced by the integration as possible, just because we want to keep Sistar-based applications fast. Fortunately, Rust compiles to object files, which can be easily linked with ones produced by C++, so we're covered there, because it's more or less a zero-cost integration. Wasmtime checks all the boxes for us, although not perfectly. It has asynchronous support based on a concept of fuel. Fuel is a synthetic unit that gets consumed during WebAssembly execution, and once the executor runs out, it yields the processor. And then its virtual tank gets refilled, so long computations are split into smaller pieces, which is what we want. It also allows overriding the default allocation routines for executing WebAssembly, but as far as we know, it still uses its own allocation schemes based on mmap for internal data structures. Hopefully that will change, or we'll just send a patch, because Wasmtime is open source and also actively encourages people to contribute, and we're very much into open source collaboration. Now, asynchronous Rust looks deceptively similar to the C star model, if you're familiar with it, because both are based on futures. But the resemblance is actually superficial. C star's future is a representation of an ongoing asynchronous operation, and as soon as the future is created, its corresponding task is also queued in the reactor. In Rust model, future is the computation itself, and it does not do anything on its own. It can be thought of as a state machine which exposes a function, poll, which is capable of transitioning the future to its next state. Something needs to call this function though, and in Rust nomenclature, this runner is called runtime. The most popular de facto standard runtime is Tokyo, which is quite feature complete, has a huge open source community, and is generally a fantastic default choice. That's also the runtime we rely on in ScyllaDB Rust driver, by the way. Now, how are asynchronous projects customarily implemented in Rust and in C++? In C++, the usual flow is to pick a framework like C star, or Boost Asio, or libuv, or any other available library, and then start coding in it using its specific idioms, be it callbacks, futures, whatever the framework implements. In Rust, the situation is a little different because technically you can express this asynchronous state machine without ever actually running it, and it still compiles to useful code. Usually there's no point in implementing async Rust functions without just calling them by runtime, but we do see a point, and this separation is what lets us integrate code written in async Rust seamlessly into a C++ framework without having to instantiate two separate runtimes or reactors. Note that Wasmtime also exposes C++ bindings and a C library for people who want to integrate with it, which is an alternative approach where you just take this library and use it in your C++ project. However, this library is not as feature complete as native Rust code, and most importantly, it doesn't offer any async support, which was crucial for us. In particular, the async Rust code that we implemented for running user-defined functions in WebAssembly is computation only. What that means is that there's no input-output. We do not need any disk access, no network. There are no injected delays. The code simply needs to carry out quite long calculations, which involve compiling and running a WebAssembly module. This class of computation-only features are extremely useful because the following assumption holds true. Each polling of such feature moves the computation meaningfully forward. This is not necessarily the case when we need to wait for a disk operation to finish, or wait until we receive data via a network socket, or there's a delay injected in the code for some reason. But here we just proceed with executing machine code, so the call to poll is never wasted effort. In general, Rust runtimes, so the libraries that run asynchronous functions, are quite complex projects because they need to be general purpose. They need fair schedulers, make sure that no tasks are stalled or starved, that there are no deadlocks, that latency is reasonable, that we do not busy poll on disks and network sockets too much, and so on. But if we assume we have just a single function which only performs computations without any input-output, the matter becomes quite trivial. We just need a loop which constantly polls the future, proceeding with the calculations until it becomes ready, which signals that the computations are done. And that's it. We finalize the computation successfully. With that knowledge, we can write such a runtime in C++ too. If we just expose a symbol from Rust, which allows us to poll if the future is ready, and also move the computation forward, we're done. And note that with such a simple runtime, we can also safely optionally yield the processor after each step, which makes this minimalistic so-called runtime latency-friendly as well. Each small step is expected to finish in reasonable time, so even if the total execution time is long, other asynchronous tasks are free to use the processor as well. It's especially important if there are high priority tasks in the queue, because we wouldn't want to block them for a long time with a user-defined function execution. This is why I mentioned that WASMtime, the WebAssembly runtime of our choice, has great async support, and that we appreciate it. It includes the ability to split the execution into smaller pieces, and only a single piece at a time will be executed in this single step of the state machine. Now, C-star is a C++ framework, so if we implement the user-defined functions layer for ScyllaDB in Rust, we also need to be able to combine the compiled code into a single runnable binary. Fortunately for us, bindings from Rust to C++ can be quite easily developed. Rust supports an extern C mechanism, which allows the developers to export C symbols, which can then be linked with compiled C++ code. But there's also a fantastic CXX crate, which helps with the interoperability effort. It's very nice because it also supports type translation, including unique pointers and Rust's box type, translating Rust's result enum to functions throwing exceptions in C++, and is generally extremely convenient. Plus, it's more or less a zero-cost abstraction because the type translation needs to be done one way or another. We went with CXX instead of open coding the bindings ourselves, and we do not regret the decision at all. It made the development way more productive. And the next step in integrating our new Rust code with C-star-based core of ScyllaDB is writing this very simple runtime I mentioned a few slides before. It has some extra lines compared to the original pseudocode, but this is actual working C-star code capable of running the linked Rust machinery, which computes the user-defined function written in WebAssembly. Here, the Rust part is represented as the UDF computation variable, and the rest is just a little bit of boilerplate to run the future. This code is also not likely to cause reactor stalls because it periodically yields the execution and allows other background tasks to make progress as well. To sum up, our architecture is as follows. We have rewritten the whole layer responsible for running user-defined functions from C++ to Rust based on the WASMtime crate, which provides the WebAssembly virtual machine implemented in an asynchronous manner and yielding CPU if the computations take too long. This code is linked right into ScyllaDB, where it is polled in a latency-friendly manner. And that's it. We managed to seamlessly integrate asynchronous Rust code into an asynchronous C++ framework, and there's no needless overhead. The Rust code compiles to a state machine, and we can utilize that state machine right from C++. And that's it. Thanks, everyone, and feel free to reach out to me should you have any questions.